This is part 3 of what I like to call guided dialogue. Maybe even in the style of Socrates, Plato, and Aristotle from long, long ago. Maybe a Socratic dialogue where you have an expert, the Socrates person, who asks a series of questions to draw out the good answers. Part 1 of the dialogue was just starting a cold introduction to projectile motion. Now, normally projectile motion is done in most physics classes early in the year before you know anything. Well, I waited this time until the full semester had finished. We'd taken the midterm exam. They knew everything from a full semester of physics, and now they're going to cold apply all those ideas to projectile motion. That's part 1. Part 2 was after some reading. They'd gone home and done some reading. We introduced the problem solution style for projectile motion. Now, this is part 3, and it's the summary of all of it together. This is day 4. They've solved some problems already. We've had some additional dialogue. If you haven't seen parts 1 and 2, go see them now before you see this one, because this one doesn't make a whole lot of sense without that. And, well, I'm going to start off this time, happen to have a discussion with my students about my experience in New York State and the New York State Regents exam, similar to our Pennsylvania Keystone exams, but they've been doing it for 150 years and close to 100 at the high school level. A state exam for New York State, the Regents exam in earth science. I took one in biology, I took one in chemistry, I took one in physics, I took one algebra 1 and geometry and algebra 2. I took 3 math tests. I took calculus my senior year, which wasn't tested statewide. After 3 years, I took a literature test. After 3 years, I took a social studies history test. And then I took a Spanish test, and that's it. So those were all the Regents, the statewide exams. Now, in order to cover all the material for that statewide exam, you have to cover a certain amount of material, generally in a particular way. There is a prescribed curriculum. However, here there isn't a prescribed curriculum, and if your administration doesn't force you to teach exactly this particular way, you can experiment and do things differently. And as I mentioned to you before, all the books pretty much will put this fascinating projectile motion stuff at the very beginning before you know any physics, which is just, it's dumb. It's a dumb place to put it, because there's some really good applications here. And this is the first time that I've taught it really after the midterm in this way, because you've already done all this other stuff. And I just wanted to see how well you picked these things up and how well you were able to apply it, knowing perfectly well that many of your answers would have been completely wrong. But that's another one of the things that we don't do as teachers. Being wrong is fine. We have to teach our students and remember ourselves that being wrong is entirely acceptable. We need to constantly attempt to learn as much as we can, to risk, to fail, and then to learn. Because without that risk and without the failure, there isn't as much enduring learning as we want. So I ask a lot of questions about definitions and equations and units and all kinds of things like that to bring it all together. Some of these things they don't remember, but then they do. And I have to ask them individual questions to make sure that they do remember it and that they are constantly challenged and that they're constantly engaged in thinking. We got into teaching because we like you. I mean, I didn't. But we got into teaching because we like our students and we want to be warm and welcoming and we want our students to learn and feel good about learning in our classes. Well, I know perfectly well that when you feel good about your learning, you're not necessarily learning anything because, well, you feel good about watching a video. You're like, oh yeah, I learned so much in watching that video, and the before and after tests, nothing. You didn't really learn anything. Now, obviously, if you're watching this, you're watching a video. However, I have done tests on my students with pre-knowledge and post-knowledge after watching even a 2-minute video in class. Okay, here's what you know, here's what you don't know. You're going to watch this video, all the answers are given, and then I'm going to post-test you. And, well, it turns out that my students don't learn a whole lot from watching videos. I don't think I learn a whole lot from watching videos because sometimes we go so quickly, especially the more entertaining ones, those really cool science videos. They're like, oh, they make you feel really good, lots of colors, lots of things, feels like you learned something. but you probably didn't learn as much as you wanted to. So go back and watch that 5 times, and every single time you're going to learn something new. Read a book instead, or preferably read a book, because books, so much information packed into a smaller time period, because you can read a whole lot faster than you can watch a video, and you have to engage with the book. You have to. With the video, you can kind of sit back and maybe listen a little bit, but nah, with the video, with the book, you learn a lot. So get reading books, because that is a significant source of my learning of everything. And when I ask you specific questions that are designed to elicit specific answers, and I don't go like off the reservation and ask you all kinds of like really completely vague things, which I tend to do, but most people don't, and questions that have like a whole bunch of different possible answers. When I don't do that, it's not the best for your education. And so what I do is ask you lots of other random things that happen to come to my head at that moment and see what you do with it. Some of you do really well, some of you do really badly, but you get better at it as time goes on. And that's the thing. So at first, you teach a whole bunch of things, you learn a whole bunch of things, you now have a whole bunch of physics knowledge in your head, and you're supposed to now apply. Generally, the main goal in projectile motion is to be able to solve problems, and perhaps even to solve some real practical problems, like my one-shot challenge that I have my students do. It's a great thing. We got this projectile launcher, and they have to take the ball and launch it into a bucket. And they have to decide where to place the bucket, given measurements that they take. It's actually pretty cool. And sometimes entire classes make it in, and sometimes entire classes completely miss. But got a video on that one too. This is a problem. So I'm setting them up to do this one-shot quiz, which is 10 points, all or nothing. And it's pretty cool. But this is a problem to help them set it up and get their brains again and again and again into solving different kinds of problems. Okay, so here we have the problem. This is a problem you did a couple of days ago. So the problem we started with, you had 300 meters per second, third into 63. Do you have this problem out in front of you? Because some of you do already. So problems should be out in front of you, 63 degrees, 300 meters per second. That's pretty funny, because it's like 700 miles an hour. But how much air friction is there? 0. None. 700 miles an hour, cannonball flying through the air, 0 air friction, which is funny. It's just, but we have to eliminate that to make it what? Easier. Make it easier. So the thing's flying through the air, lands 100 meters above the launch point, and your job is to find this horizontal displacement. All right. So now you can throw the ball around again. So you ready to catch the ball? Are you ready to catch this thing? Are you? What? You're supposed to be ready to catch it. Come on. Okay, so the ball gets thrown around. And this ball, as it is thrown around, and the ball right here, all of these objects, the projectiles, as the little projectiles, as they're flying around, tell me about the forces acting on it. Peter, what are the forces acting on it?
The weight down.
The weight down. You only have the weight down. That weight down is what kind of force?
It's the net force.
It's the net force. So that weight is the only force. It is therefore the net force. What is that weight, the net force, doing?
It's accelerating it vertically.
It's accelerating it vertically. Because, well, how do you know it's accelerating it vertically?
Because it pulls it down.
It pulls it vertically, so it's accelerating it vertically. And that's the nature of Newton's second law, right? What is Newton's second law of motion?
Net force equals mass times acceleration.
Net force equals mass times acceleration. Let's write that thing down. And what is acceleration? Marissa, what's acceleration?
The rate of change of velocity.
The rate of change of velocity. And that rate of change of velocity, the acceleration, once again the question, what does the weight do?
The weight accelerates the ball down.
The weight accelerates the ball downward. Keep going. I mean, you said something else that I didn't hear. That's why I'm saying keep going.
I don't remember what.
Nothing else? Okay, get back. Okay, so the weight. What is it doing? What's the weight doing?
It's causing acceleration.
We already have that answer. Keep going. More. What's the weight doing?
Isn't it a net force, so it's causing an acceleration?
Okay, that's the fourth time we heard the same answer.
Okay, okay.
Come on, give me some more, give me some more. It is.
Okay. Okay, so okay. So that means it's only the vertical velocity that is changed. Well, yeah, I'm trying to move along, but it's only the
True, okay, true. So it is the vertical velocity that's changing. And you represented that up here because in the x column, Denny, x column, what acceleration is there?
there's no acceleration.
No acceleration, because you know that the weight and the acceleration necessarily parallel to each other. That's the nature of Newton's second law. This net force and its direction causes that acceleration in that direction. Okay, so more. What does that weight do?
Constant acceleration.
It is a constant acceleration. It is vertical. It is, again, an acceleration. Okay, more. What is that weight doing?
Wouldn't it be changing its tangential velocity?
It is changing the tangential velocity. And it is changing that tangential velocity in what way?
Changing its direction.
It's changing its direction, and it is changing its speed. It is changing its speed, and it is changing its direction. And since it's changing its speed and its direction, so the weight is actually doing that. How is the weight changing its speed?
Because in the y column, the acceleration is 10 meters per second or something.
True, but we're talking about just the changing of the speed. Rather than splitting it into the components, we're just going to look at the speed of the thing. So it starts out, where is it traveling the slowest?
At the top.
Top. So it's traveling the slowest at the top. And that's for everyone, this is, the speed is what to the curve?
And
Tan weight. Tan weight.
tangent, it would be.
Tangent. Is the speed tangent to this curve?
The speed doesn't have a direction because it's not a vector.
Oh, that's good. So going back to a definition, the speed doesn't have a direction, but is the velocity tangent to this curve?
Yes.
Yeah, so the velocity is tangent to the curve. It's shortest up here, and where's it longest?
Towards the bottom.
Towards the bottom, if she's talking about here. So longest here, and then a little shorter, and then about the same length as that one, and then probably be the longest at the lowest point, right? So that tangent, and that tangential velocity, the magnitude of it, the length of it changes, gets smallest, and then it increases. And does that weight cause the change in that length?
Yeah.
Does the weight cause a change in length?
Yes.
Yeah, how?
If you split the weight into two components, one of which is facing towards the center and one of which is tangential to the parabola, then that gives you two different acceleration.
So you have the weight is doing all that stuff. It's the only thing that can do this, right? So the weight is causing the change in direction. And what do you call that change in direction?
Centripetal acceleration.
Call it the centripetal acceleration. So is there a centripetal net force that causes that?
Yes.
Because you know that the net force causes all the accelerations in the universe. And if there is at this point, because it is changing direction, like right there has to be a centripetal net force that causes the centripetal acceleration. And is there also a tangential net force that causes the tangential acceleration? Yeah, so there also is a tangential net force that causes the tangential acceleration. And the two of those, because you know that it's slowing down on the way up and it is changing direction. There it is. That's the weight. The weight causes both of those. You got an object on an inclined plane, and here is the free body diagram. The weight, and I'm only showing the weight here to show the components. The weight straight down, and then there's a weight component perpendicular and the weight component parallel. We use that concept for the projectile. For projectile motion, you have, well, exactly one force, and that is the weight. And the weight has a perpendicular component and a parallel component, just like the inclined plane. And the parallel component is the net force, if there's no air friction. That's the net force tangent to the curve. The tangential net force that causes the change in speed. And the W perpendicular is the centripetal net force. That component causes the change in direction. And up at the very, very, very top, as you see, there's just the weight, because there's only a change in direction at the very top. And then as it crests and keeps on coming down, the weight is split into two components. And as you come down farther and farther, the weight component parallel, the tangential component, is larger. And so it picks up speed at a greater rate, and it changes direction at a less rate, at a lower rate. And here you go. That's why you have the shape of a parabola, too. When you were dealing with inclined planes, you have the weight being split into the component parallel, and the component perpendicular, and you get the normal force and the friction and all that. That's exactly the same concept. So here we have this relatively complicated thing. This is a situation in which you are changing direction. But is this a circular motion? It's not circular motion, because previously, when we dealt with Newton's second law, the first time, it's all speeding up and slowing down, gas pedal, brake pedal stuff. That's the tangential acceleration. But it's constant. We dealt with constant accelerations. Is this thing speeding up and slowing down at a constant rate? No, because it's slowing down and speeding up, and up at the top, that weight is only causing the change in direction. It's exclusively centripetal. And the curve, is that a constant curve? It's not a circle. None of the stuff is circular. It's not linear. It's a massively complicated combination of centripetal and tangential. Or at the very top, it's only centripetal, because the only force that we're really dealing with is that. Try to make it as simple as possible for you solving problems. Now, we can use those weight components to solve the problem, but it's a whole lot more complicated. We can use Newton's second law to solve the problem, but it's a lot more complicated with those two. So anyway, what we do to solve problems is different from what we do to really understand the situation. Those free body diagrams and the tangential net force and the tangential acceleration and the centripetal net force and all that stuff helps you understand why the trajectory of a projectile is a parabola. Crazy words. Because it's changing direction the most at the very top and changing speed the most at the bottom, because the ratio of the components changes as you go around. But that's really complicated. It's good for pictures, it's good for understanding, but you can't solve a problem easily that way. So what we do is split it into the x and y components. Split that projectile velocity into the x and y components, and knowing that the x doesn't change because there isn't any force in the x direction with no air friction, and the y does change because that's the only force, we can solve problems this way using our two-column format. So when you solve this problem, because you have the problem out in front of you, when you solved this problem, 300 meters per second, the x component, the y component, what's the x component, the y component of this?
136 and 267.
136, 267, acceleration is 0, acceleration is negative 10 meters per second every second. And why is that negative? Callie, why is it negative?
Because the weight is downward.
Because the weight is downward, and that thing is caused by the weight, and the weight is down. Well, why don't we use a negative rather than just a down arrow?
So in our equations it has that.
Because it's the only way we can do it in the equations. Because when in the equations you have up and down, this is just a two-dimensional thing that we're dealing with. You have to put it into an equation as either a positive or a negative, because you can't put an arrow into an equation and actually have it work. I grew up, for the most part, in New York State, and as a result, had to use the New York State curriculum, and we took Regents exams at the end of every class pretty much in high school, and it was really good. It really prepared me very well for college. There's serious advantages to that, but this kind of lesson is difficult to do with a scripted curriculum or with a huge amount of information you have to put into a regular standard Regents class. really difficult to do. But, you can do some of this stuff at least, and you should be doing some of this, because especially for a class where you're tested at the end of the year for the entire year of information, you really need to constantly review and make sure that they know everything. And this is one way to do it, but you can't do it as much as perhaps you would like to. One thing you're going to have to do, though, is make sure that you are not giving PowerPoints on a regular basis. If you are giving notes in class by PowerPoint, it is slow, it is ponderous, it is annoying. I can't stand it, your students don't like it, and it's not good. If they are at least of the level where they can take notes outside of class, you just have to have that. They're taking notes outside of class on maybe a video, not so good a video, but we have a textbook. I have them take notes out of a textbook. I did that between day 1 and day 2, video 1 and video 2 of this series of lessons. And it worked out really, really, really well. And I've done this for years now. Have them take notes in a good outline format, whatever format you want to use. And then when they're done taking those notes, then they come in and we have a big discussion, and all those ideas, you ask them individual questions of all the stuff they need to know, and they have their notes out in front of them. Maybe you give them a quiz when they walk in to make sure that they gleaned the appropriate information from those notes that they took. Then you can work with that. But you have to push that note-taking stuff outside of the class so you have time for the good stuff. Some people call that the flipped classroom. It's good teaching. In my opinion, you have to do that. We've been doing this for thousands of years. You just go do something outside of class, come in, we'll discuss it. Guided dialogue is really good. You have to make sure also that you question individuals. Everybody's got to be involved. All these students in the class have to be involved in the discussion. They have to know that at any moment they might be called on. And you call on the good, the really good, strong students for the toughest questions. But everybody has to know the definitions, and everybody has to know units, and everybody has to know the stuff we've gone over already. So as time goes on, you ask more and more questions of more and more individuals, and they do more and more of the actual work. It's a good way to keep everybody involved and make sure that they are learning. Some say you can't make anybody learn. Well, yeah, you can. Do it this way, and they learn, it goes in their brains, and it stays in those little brains. Thanks for watching Learn Physics. And thanks for that thumbs up too. Really helps a lot. New videos most academic weeks. Subscribe for more. I've even got education ideas, Freaky Physics Friday, and Tech Tip Tuesday. And for bicycles, motorcycles, and family adventures, it's my other channel, Bike Physics. You just learned physics.